82 watts. That is quite the improvement. Let's see how we got there. This is a buck converter from China. And as you can see, it allows me to change the amount of power that reaches the lamp from the power supply. But I want to make one for myself, so I can control it electronically instead of using a screwdriver. And I did. In previous videos, I was able to control up to 50 watts of power with a breadboard circuit. But I want more power. So now we are here, my fourth attempt. This is the circuit I am building. It is a hand-drawn copy from Wikipedia. And this is the circuit drawn in an online schematic editor. From that I built a PCB, which I also ordered online from China. I really wanted to build this on a prototype board, but this PCB step is necessary. I will explain why when we get to the tricky part, the flyback diode. Let's build this board up one piece at a time, and I will explain each component while we are at it. Alright, I have my board, components and soldering iron ready to go. The input terminal will be connected to the input power source, in my case a bench power supply, but eventually these will be connected to a 24-volt battery. I am planning to use this circuit to control the amount of power going from my solar batteries to my grid-tied inverter. The spacing of the holes on the PCB do not match the spacing on the terminal pins. This will happen more than once, and I will take notes so that I can edit the PCB for the next video. The input capacitor's job is to keep the input voltage stable. Even though the power supply has its own capacitors, or maybe even is one, like a battery, it is important to have one close to the circuit. That is because it is a storage of power close to where we are using it. It will prevent sudden changes of current in the supply wires, and that saves power and prevents heat generation in the wires. I find it rather difficult to get the pins hot enough for soldering. This is because the large amount of copper on the board attached to it. There is a lot of material to heat up. Again, that will also be explained when getting to the diode. A MOSFET is a non-mechanical switch, and in this circuit it will switch the load on and off very fast, and for a specific amount of time, so we can control how much power the load will get. Imagine turning the light on and off so fast you can see the switching, but you can notice it's less bright than normal. Some circuits accept this directly, like a lamp, but most will not. Which is why we will add an inductor after this. The MOSFET also needs a heatsink, and in this case the mounting holes don't match. So I need to rework that also for the next iteration. For now, I will just remove the mounting pins. I found myself some thermal paste and add that to the heatsink. Oh wait, can't get the lid off. Really sucks when that happens. There is a cutting tool in the cap. Excellent. Now I just screw on the heatsink with whatever bolts I have lying around. This is an inductor, but not the one we need. So I will make one myself. I bought some cores from China, and I already experimented with it, so I know how many turns of copper I need to wind around it. So, what does the inductor do? Well, it is a sort of electric flywheel. Send electricity through it and it spins up. It stores the energy. And when we are done doing that, it will return the energy to the circuit if it can. Like it just became a small battery of its own. Because there is a diode in the circuit can still provide a path for electricity to flow, even when the MOSFET is closed. And because the inductor takes time to power up and down again, we get an average amount of current sent out. That is something any circuit can handle. How many inductance do we need anyway? Controlling it with an Arduino, with something like 50 kHz of switching, 20 to about 100 microhenry. If unsure, keep it higher. We can fix a lot with software by adjusting the switching frequency in order to match the inductance better. As you can see on the board, this is not my first attempt. Well, that's how life goes sometimes. Soldering an inductor in is not that easy. Lots of copper that sucks the heat out of the solder, and also makes the inductor hot to touch at some points. The story here is the same as with the input power supply. Store power locally to prevent current swing in the output wires, keeping things cool and efficient. I want to keep the driver board separate from the switching board. That way I can experiment all I want without having to change the entire board every time. When the MOSFET is turned on, we have a completed circuit to power the load, and also charge the inductor at the same time. Then, when the MOSFET is turned off, the inductor has energy stored and becomes a power supply of its own. This is where the diode comes in. Power cannot short to ground during charging. That's blocked. But power can return to the inductor when needed. Why a PCB and not a breadboard or prototype board? Well, the first two versions were indeed on a breadboard. And that went well up to around 50 watts of load. At that point, some wired connections on the board started to get really hot. So then I switched to prototype board, thinking that would solve all my problems. The wired connections were almost twice as thick, but also twice as long. Problems got worse. My driver IC kept getting destroyed, and it took me quite some time to figure out why. Alright, here we go. In short, I created a lot of unwanted inductance in all the new long and thin wires. After the MOSFET turns off, the inductor tries to release its energy, with the exact same current as it has seen last when charging. But at first the diode does not conduct. That only happens when the difference on both ends is greater than a fraction of a volt. So a non-conducting diode means no amps can flow around. But voltage is the result of current times resistance. And the resistance is high, infinite even. Thus voltage should also shoot up extremely high if we follow that formula. That means the voltage over the inductor starts rising. Now, because the positive side of the inductor is connected to the output capacitor, that side's voltage is fixed. And that is why the negative side of the inductor, which is also the source of the MOSFET, drops below ground and keeps sinking until the diode finally allows current to go around and solves the problem. But then there is me, with my long wires. Because of the length, they start to behave like an inductor, storing part of the energy and slowing down the voltage change at the other end. So the dropping voltage on the source part of the inductor MOSFET combo does not reach the diode immediately. And when it finally does and the diode starts to conduct, current from the output capacitor also takes its time to flow back to the diode. And then to the inductor MOSFET. So there are 3 delays in total before the voltage at the inductor starts to recover. Now, because the driver IC is very close to the MOSFET, that source there drops more than 5 volts below ground, before the diode tries to straighten things out. And the IC can't handle that difference, so it gets destroyed. The solution? More copper for each connection between components. That means less induction and resistance, and so less echoing or ringing of power. I have tried that on a prototype board, as you can see, but that didn't work. That would have to be applied to every high power connection, and that would have become a mess pretty quickly. So I built a PCB, and I made the backside of the board all ground. An entire plane, as they call it. And I did the same for the top side. Separate planes for each high power connection. ChatGPT did not agree with that last part, but could not really explain why ground could be a plane and anything else couldn't. In my opinion, ground is not a special kind of electricity that has exclusivity to being a copper plane. Stupid AI bots. So here we have it. Top side of the board cut into multiple copper regions. Hope you like it.